Welcome back to Business Analytics Using Forecasting. I'm Galit Shmueli. In this third video of the 3 videos on performance evaluation, we're going to look at performance charts and performance measures. Remember, the question that we're trying to answer with this whole exercise is, how well is our forecasting model going to work in practice? We're going to try and find out what is the forecast accuracy of our method, but remember always that we care about the practical implications of the forecasts. How do we actually find out how well the model is working? We're going to start looking at the validation period. Remember, that's the period where we closed our eyes and pretended it was the future and we don't know the values. And we're going to look at a pair of charts. We're going to look at the actual values that we closed our eyes to, and we're going to compare those to the forecasted values that we generated from our model. By comparing these two numbers, we can see how well our model is forecasting values that it did not see. The other type of chart that we're going to look at is going to look directly at the discrepancy between these two numbers, the difference between the actual and the forecast. That's what we called the forecast error, or the residual. So we'll have 2 charts. One chart will have 2 lines on it, and the other chart will have a single line on it. And you'll see how the pair of charts each highlight different aspects of the forecasting performance. Here's an example of the data that we saw earlier about ridership on Amtrak. The black line is the actual monthly ridership. The blue line is the naive forecast, if you remember. The top chart has T, or month, on the x-axis and ridership numbers on the y-axis. And what we can see here is how closely our forecast line follows the actual line. The other chart that's right below it and has the exact same x-axis is the residual chart, or the forecast errors chart. Notice that the y-axis here is different. This is measuring the error, the difference between y and f. Ideally, we would want everything to be 0, but obviously that's impossible. So what we can see here are over-forecasts and under-forecasts that are much easier to spot than in the original series. However, the original series helps us see what are the magnitudes compared to the numbers that we're talking about. Is a big spike here really big in terms of ridership numbers, or maybe it's not so important? This pair of charts is very useful to generate in every model that you create, including naive forecasts and more sophisticated models. Recall the question that we asked earlier: is the best fitting model the best forecaster for the future values? And the answer that we reached was no. You can see now that we're talking about the training versus the validation periods. If you fit your training period very, very tightly well, this same model is probably not going to work so well in the validation period. So how can we find out whether we're overfitting? The answer is we can compare the performance in the training period to the performance in the validation period. The previous charts that we looked at were for the validation period, but I can generate the exact same pair of charts for the training period as well. Here's a chart that shows me both the training period and the validation period for the same data. The validation period charts are what we just looked at. Now I'm adding the training periods. And this is where we can see whether the errors get much worse in the validation period or not. If they're kind of similar in magnitude to the training period, it means we have not overfitted our original series. So these pairs of plots are useful for 2 reasons. One is for evaluating predictive performance by looking at the validation period, and the other is for assessing overfitting by comparing the validation performance to the training performance. In addition to charts, there are common metrics that software generate for us. And I'd like you to be familiar with these types of metrics, but also be a little wary about only using metrics. It's much easier, but you know a lot less. Here are the common metrics that are used in forecasting. They're also commonly used in other predictive applications. Remember, we have our errors, E sub t, and I can compute errors for my entire series and take the average. If I take the average, it's just called the average error. I can compute the average error for the training period. I can compute the average error for the validation period. Then I can look at some other functions of the error. I can say, maybe I don't care about the direction of the error. Did I overforecast? Did I underforecast? I don't care. I just care about the magnitude. In that case, I might look at the absolute value of the error. And then I look at the absolute values of each one of my forecasts and take an average. By taking that average, we get a metric called the mean absolute error, MAE, sometimes called the mean absolute deviation, or MAD. Another type of metric that we use is based not on the absolute error, but on the squared error. The squared error will not only remove the sign, so again, like the absolute value, we don't care about under or over forecasting, but the square also penalizes big errors. If you have a very big error, it gets huge. And averaging squared errors gives us a metric called the mean squared error, or MSE. And sometimes we take a square root of this MSE, which is called the root mean squared error, or RMSE. So software might give you MSE or RMSE. They're basically the same idea. The reason to use RMSE is that the value will be on the same scale of your original data. Finally, another very common metric that you'll see in performance of forecasting methods is called MAPE. And what is MAPE? MAPE looks not at the error alone, but it looks at the error as the percentage of the actual value. And this gives us an idea about not only the error magnitude, but the magnitude relative to what we're measuring. We'll get numbers such as 5%, 2%, and that is the average error. The idea, again, is simply compute this value for every time period, and then simply take an average of these absolute values. These are 4 very common metrics. You might see somewhat other metrics in other software, but the idea is, again, taking the errors and accumulating them in some way. Let's see how we do computations with these metrics. For example, we have our data for the Amtrak ridership. We have the forecasts, we have the actual values, and we have the forecast errors, which are simply the difference between the actual value minus the forecast. I can compute errors and take their average. That will give me the average error. In this case, it ends up being negative 34.14, just the average of this column. Or I can compute the mean absolute error by taking absolute values of these figures and then taking an average. If I want an MSE, I will square each one of these values and then take an average. And similarly for MAPE, I will take each one of these forecast errors and divide them by the actual value, then take an absolute value and take an average. So a very simple example, these types of calculations can easily be done in spreadsheets or in any other software where you're writing the functions. Software will typically give you some kind of measures, and as we talked about earlier, you hope to get these measures separately for the training period and for the validation period. When we look at these numbers for the training period, what it's measuring is data fit. How closely did the model fit the data that we used? When we look at the same metrics for the validation period, it's measuring predictive accuracy, because this is how well this model is predicting data that it did not see. So we're measuring 2 different things here. And that's why we use these numbers to say something about how well this model will work in the future. And we compare these 2 sets of numbers to make sure that we did not overfit the data. If we overfit the data, we expect the numbers in the validation to be much worse than the ones in the training. Obviously, they will be slightly worse, but the question is if they're order of magnitude different. Software will give us performance metrics that are separate for the training and validation periods. Remember that the validation period is the time where we did not look at the data. And therefore, when we're looking at the numbers, the metrics for the validation period, we're measuring predictive accuracy. How well did our model predict a new period that it did not see? In contrast, when we look at the training period and the metrics up here, we're looking at how well the model fitted the data that it actually did see. And therefore, the training period is measuring data fit. It's not measuring predictive accuracy. When we want to talk about predictive accuracy or how well this model will likely work in the future, we're going to look at the numbers over the validation period. We're going to compare these two, the training and validation numbers, for evaluating whether we overfitted the training period. In that case, we're going to see a big discrepancy between the numbers for the training period and the numbers for the validation period. Most of the times, the training period numbers will be slightly better, but the question is, do we see an order of magnitude difference between the two? I will repeat again that measures like this are very easy to generate with software, but they have their limitations. First of all, there are a few challenges that they face. For example, if we have missing values in the validation period or in the training period, then it's not clear what do we do with those periods. We can just say, let's exclude those periods and compute the metrics taking averages without them. That's one option. Another problem that happens is when you have zero counts. Sometimes you're measuring something that at some periods hits the number 0. And if you remember, one of our measures called MAPE is based on an absolute percentage error where we divide by the actual number. So if we have actual numbers of zeros, we cannot compute MAPEs. So zero counts also produce some challenges for these metrics. These are technical challenges. The bigger problem is that the metrics hide more than they actually show us. And that's why I always advocate create the charts. These performance charts tell you a lot more than just the metrics alone. What the metrics can give us an idea is a quick idea about overfitting, a quick idea about average predictive performance, but they don't tell us what went wrong, and more importantly, it doesn't tell us when it went wrong. When we create a chart, we actually can see where things are going wrong. So when will I use these metrics? For example, when I'm trying to forecast a really large number of series, and maybe this is an automated system that's going to be running, and I can't look at so many charts. That's when metrics like this are very useful. But if you do have the time, and especially while building your models, looking at the charts is going to make a huge difference. This pair of charts, actuals and forecasts, and forecast errors, really help you understand when things are going wrong, and maybe sometimes why things are going wrong. This is all about forecast accuracy, but this does not directly take into account the business problem that you're trying to solve. For example, one common consideration that you should have is costs. Maybe there are different costs to different types of mistakes. Maybe when you have very large errors, you pay a huge price versus smaller errors. Maybe you just care about a threshold if your forecast errors are above a certain number or below a certain number. I don't care what exactly is the magnitude, just the threshold. A different consideration that is very common is, do I care about over-forecasting differently than from under-forecasting? Sometimes one of these has more serious implications than the other. And you'll find that in some cases, some stakeholders worry more about under-forecasting, while others care more about over-forecasting. So all of these types of criteria, you cannot really gauge from metrics. The charts can help you think about them, but you will have to directly think and plot and consider costs when you're building your forecasting solution. You might even build a cost function and see how much your forecasting solution is going to cost you when you deploy it. Here's an extreme example from an earthquake that happened recently in Italy. The people who were producing the forecasts about whether an earthquake is going to occur or not are actually sitting in jail right now because they weren't able to forecast that this earthquake was going to happen. So in their mind, the forecast accuracy, what you really care about is making the mistake of not forecasting an earthquake when in fact there is one. But if you think about someone else, such as citizens or maybe the government, maybe a different type of cost would matter more to them. So considering the entire context is crucial to really measuring the performance of your model. We talked until now about generating a point forecast, a number. That f sub t plus k is one number. But clearly, when you give me a number, I think that that is the number. And that's the problem with only giving stakeholders point forecasts. What we're not conveying is the uncertainty that surrounds that forecast. And that's why it's very useful to not only report a point forecast, but also report a prediction interval. A prediction interval is a probabilistic statement. For example, a 95% prediction interval is an interval that has a probability of 95% that the actual value will be in a certain range. By giving me an interval, I have a better idea about the uncertainty that I have about a certain forecast. There's a theoretical formula which can be used in some cases, but as we'll see soon, it's a little challenging to use it. The idea here is based on the normal distribution. And if we can assume that our forecast errors follow a normal bell curve distribution, then we can use just a very simple formula that says, take your point forecast, estimate the standard deviation, and then just add a few, one or two standard deviations around it. That's a typical, like a confidence interval. This will work very nicely if indeed the errors follow a normal distribution. The problem with using this formula is that many times the errors that are generated by forecasting models are not normal. And if your models are biased in some way, then building a symmetrical prediction interval around your forecast up by 2 standard deviations and down by 2 standard deviations is not going to give you the right idea about the uncertainty. So that's one problem. The other problem is that if you think about how do I estimate the standard deviation, I need some errors in order to estimate the standard deviation. Where do I get those errors from? From the validation period. But the problem is the validation period is typically very short. If we do roll forward, we have a little more validation data, but typically we don't have a lot of data. So our estimates of the standard error are also not going to be very good. So these are the challenges. What can we do? One option is to take the errors, and if they really look like they're non-normal, do some kind of a transformation. Something like a log transform, or if you know what the Box-Cox transformation is, you can try that. A different solution is to build an empirical prediction interval, basically looking at the distribution of the errors and then finding percentiles of that distribution that will give us a 95% prediction interval. Let's look at a little example. Here's a histogram of a forecast errors from a certain forecaster. And we can see clearly that the histogram is not symmetrical. It's missing the right tail. So we have a left skewed distribution with forecast errors going all the way down to -400, but only up to 300. Since it's not normal, we can either transform the data and then use the theoretical formula, or I can take this distribution, this set of numbers, and compute the percentiles, for example, the 5th percentile and the 95th percentile, and then give this interval as my 90th percent prediction interval. Every software can give you percentiles. Even in Excel, we have a percentile function. So this is an option of creating empirical prediction intervals. The bottom line of this video is that performance charts and metrics are really important. We use them to evaluate the predictive accuracy on the validation period, which gives us an indication about how well this model will work in the future. And we also use them to assess overfitting and make sure that we didn't fit our training period so well that the model is working terribly on the validation period. We also talked about the issue of not only looking at metrics and not only looking at charts, but thinking about other considerations and other costs that are related to the context itself. And if you can measure those costs, or somehow convey your final outcome of interest, that is really what you want to include in your performance evaluation. Finally, we want not only to convey the forecast, the point forecast, but we want to say something about how certain we are about this forecast. And that's where prediction intervals come into play, and very useful both to compute them, to report them, and to plot them on our charts.